Okay, hey everyone, the recording glitched 3 times in a row. Luckily, I didn't get too far into the note. Welcome back to this week. We're diving into our new unit here, very similar to the last one. The last one's called Relations and Functions. This one's called Linear Functions. So we're actually looking at purely functions now. And first lesson here is going to be on slope of a line. So just a few updates on this week as well. Friday, if we were actually in class, scheduled to be a PD day. So technically, I'm not allowed to release any lessons for you on Friday, even though you're home anyways. But I don't get it. But you get a short week this week, so I'm not going to be posting any new material on Friday. So I'm going to actually move that quiz that we were supposed to have on Friday last week to Thursday. So it'll be on the off day, and it'll be about 10 to 12 questions, I imagine, and the exact same format that it's been the previous time. So just multiple choice and some short answer stuff related to everything that we've done from Tuesday last week. Okay, so nothing changed with that, just a big heads up. So let's dig in here, and hopefully I'm just going to try and keep this below 25 minutes. So let's look at slope of a line. Let's look at what slope represents. And based on the notes that we were covering from the last unit, very early on, like during that first week, you already have, even if you don't know it, you already have an intuition of what slope is, because we've talked about it very, very briefly. But we do know what, in a very general form, what slope represents. So slope, I wrote it here for my past note, which never recorded. We can say that slope is a more exact way, so emphasis on exact, that we can essentially measure a rate of change, or we can measure how something is changing with respect to another thing. So in this case, if you look at the graph over here, we're measuring a driver's change in distance versus their change in time. Okay, so we're measuring the rate of distance over time. In this case, kilometers per hour. Kilometers per hour. So the slope here is in kilometers per hour, which we can also write as, and that is also known as the rate of change. Now, the rate of change needs to have a number usually associated with it. We just can't say that he traveled kilometers an hour all day, because that's useless, right? We need to have it, well, how fast did he travel? He traveled 50 kilometers an hour that day, right? So we need ways, an exact way in order to measure this. So we've already actually looked at these, right? I've given you a graph like this and told you to describe a scenario for me. I gave you one that was on the quiz. I was talking about toilet paper in Abbotsford and why people were going crazy buying toilet paper. You've been able to describe these very, very well. And on this graph, we actually have 4 different kinds of slopes, and you might be able to have an idea as to where I'm going to go with that and how we can define what each of these slopes mean, because we've actually talked about what those slopes are before, and we're actually going to give them a more exact name as we go here. So at its basics, slope just represents some rate of change. In this case, if I asked you to describe what each scenario here means, so if we can give these some letters to represent the segments, A, B, C, D, A, B, C, D, E, and I asked you, if you recall, what's happening between A and B for this driver? Let's assume he's driving. Well, he's accelerating moderately quick, right? He's going forward in a moderately fast speed, right? The line isn't too steep. And then from B to C, we could say, well, then he really gunned it. Maybe he's on the highway here, and he's going really, really fast and covering a lot of ground. And then C to D, we said, if there's a constant slope, that means he's not moving at all. There's no change at all, right? Like his distance hasn't changed between this hour here and this hour over here. And we say that, well, maybe he went to a truck stop and stopped to go pee or something. And then D to E, well, now our slope is going down, right? This is the first time that we're seeing it go in the other direction. So we're saying that, well, maybe he's going to return home because he forgot something. And he was going there pretty quick, right? Because this is pretty steep. So essentially, we can get this kind of intuitive idea between like looking at steepness and direction of slope. So we're actually done now. We're done talking what slope represents. So let's look into the types of slope now that we can measure. So we have steepness and direction of slope. So let's look at a few examples here. And one of them, I'm just going to draw very rough grids here. Very rough grids, just like this. And I'm going to copy and paste this 4 times. And I'm just going to move it all over here, just so it's a bit more centered. Okay. So let's suppose that I drew a slope that looked just like this. Just like this. How can we describe this? How can we describe this slope? Actually, we're going to draw 2 on here. So we'll draw one in pink. We'll draw the other one in blue. Pen has been glitching for some reason. And what I want you to do is to take a minute and I want you to describe how each of those slopes are different and what's similar about them. So the similarities here is that they're both growing in the same direction. So both growing, same direction. And what does it mean if they're going in this direction? If they're growing from this left to right, from this left to right here. Let's pretend that let's pretend that we were measuring days and then profits here or money here. What would it mean that if our function went from this point here over to this point here in, let's say, 5 days? Well, that means that we're growing in money. And another way to think of that is it's positive growth. That represents positive growth. But what's the difference between each of these two? So let's look at the pink one. If we were to measure this whole thing about days versus money, which one did you think, if both of these lines represented two different businesses, which business is doing better, do you think? Just based on just looking at that. Well, it's probably going to be the pink business here, right? Because it's getting higher profits at an earlier time than the blue one here. So we can say that our pink is steeper. So it has a greater slope. And we can say that the blue is more shallow. So we can say it has a lower slope. And this tends to be the general form. So if we have something that starts to even out even more, something that goes even shallower even more, so this is an even worse business because its slope is very, very shallow, right? Okay, so there's one of them. Let's see how we can divide this up for this one. So let's look at another one here. Let's look at another one. Let's say that this graph was going like this. And then we had this one right here. And we can compare this again. Let's say that this graph represents years, and this graph represents student debt. Okay. So what do they both have in common? Well, they're both declining, right? Because if this is years and this is student debt, as the years go on, so from 1, 2, 3, 4, 5, our debt is growing lower, right? So both are decreasing in same direction, right? Another way we can call this is negative growth, right? Because we're losing our debt. Our money is going down. Negative growth. Okay. And what can we say that's different about each of them? Which one here has the steeper slope? Which one has the steeper slope? Well, our blue actually has a steeper slope, right? Because if we think about this as paying off our debt is going down much, much quicker with this guy, right? So our blue actually has the steeper slope. Steeper. Debt goes down faster. And our pink has the more shallow slope, right? Shallow. Debt goes down longer. Right? So there's that one that we can look at. So there's two types of slopes. So what we can say is we can call this, actually we'll do this at the very end. We'll label them all at the very end. All right, let's look at another one here. So right now we've covered a positive slope, right? That was this one over here. We've covered a negative slope if it goes from left to right and it goes down during that. And so now we need to cover this guy right here. So if you remember, that one's also called a constant slope. And I'm going to do this one in a whole different color. And this one would just be a flat horizontal line, just like that. And actually, let's have it connect with, let's actually have it just, because everything's come in my previous examples come from that y-axis. So this is a no change at all. We could say constant. Actually, we'll do this in green because that's what actually defines it. We'll say constant slope. So our rate of change is actually zero. There's zero rate of change in this case. And we can use this example above. Like if we're watching that guy travel in his car, well, during C to D, we look at, well, all this time is covered. So let's say between 3 and 8 hours is covered and he hasn't moved a single bit. So 3, 4, 5, 6, 7, 3 to 7 hours. He hasn't moved any bit, right? Our distance hasn't increased or decreased, right? It's just stayed the same. So he hasn't moved at all. And then we have our last one here. And this one you're not going to see too often, but I will bring it up as an example in like quizzes and stuff it's going to be just a vertical line like that. I'm actually going to do a different color. Let's do it in purple. And there's two ways to look at this. The most common way that people say is this says no slope at all, or infinite slope. There's kind of two ways to look at it, right? Because for one, this isn't a function anymore, right? This fails a vertical line test because we could draw a vertical line through this and it would touch on infinite many points. You keep drawing the line up and up and up. For this one x value here, it's got, let's say this is like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has infinite many y values for it. So no slope, infinite, or we can say what's better to write it as is we call this one undefined. So let's label these very quickly. So this one we call, this is a positive slope. This one's called a negative slope. This one is called a constant slope. And this one over here is called an undefined slope. So I could give you a question just basically telling me what kind of slope have you drawn and describe why it is that slope. So that cancels out. That cancels out our different kinds of slopes. So let's look at how we can actually calculate this, because this is going to be the bulk of all the work that you're going to be doing with this, is figuring out how to go about calculating these. All right. So let's look at this. And we'll do calculating slope. And I'm going to actually, let's just use this example again. So I'm going to copy it. We're going to paste it down here. And of course, it did not bring in the graph. That's fantastic. Okay, let's just make our own then. So let's put in our own sticky of a grid. We'll change the paper. And let's do something like this. Let's get our color scheme going again. There's our grid. There's our other grid. Okay. So we got our y-axis and our x-axis. Okay, let's plot some points here. Let's do a linear function, and let's say that we're having points from here, between here, and down here, okay? And actually, let's stick with my real color system, and we'll connect those as blue points. Maybe I want to do a better one. Or will those two work? No, let's do a better line. Let's choose a different set of points. Let's go from this point. Is that one any better? Let's just do this one. Okay. So, and let's pretend that this is, let's actually give this, a, actually, you know what? Let's make a more, instead of an abstract idea of this, let's give it a little bit more context, because I find it's easier to understand if you do that with more context. And let's say that our line was growing from here all the way out to there. Okay, so we have A, we got B over here. And let's pretend that each of these squares here is worth 1 point. So we got Y, we got X. Okay, let's figure out what we're going to do with this. So when we're calculating slope, we're essentially figuring out the change in Y versus the change in X. So on this line, if we were to give this an actual rate, because this does have a rate, because we could see that it has a positive slope, it's increasing, it's going to have a positive rate. We can kind of estimate that rate now. We need to figure out, well, what's that? What is that rate, and how can we do that? Because essentially, all we're trying to figure out is if we took 2 points on here, and this is what we're going to do. We're going to choose 2 nice points, and this is always going to be the process in how you calculate slope. Find 2 nice points on your line. When I say 2 nice points, I mean ones that will line up right where the corner of 2 boxes meet, or 2 grids meet. So there's many on this line. So let's choose this one here, and let's label that one. So what is that one? Oops. So what is that one? This is point, we count on our X, 1, 2, 3, point 1, 2, 3, 4, 3, 4. And let's choose another point. Let's say that we choose, let's go 1. It doesn't matter what other point you choose. Let's choose this one here, just a little bit further away. My pencil's really glitching recently. And let's label this one. So this is point, that's 3, 4, 5, 6, 7, 8, 9. So this is point 9. And how many are we up? 4, 5, 6, 7, 8, 9, 8. So we have 2 nice points. And the nicer your points are, the more accurate your slope is going to be. That's also why we choose these. And what we need to do, we need to figure out how much does x change in this direction up to our 2 new points. So how much does x change? Let's do this in yellow. So what is the change in x here? And what we can say is, another way to write this is delta x means the change in x, or a little triangle in x. And what is the change in y? Change in y. And what we're going to do to figure out a rate, so remember, let's just call this side, let's call this side kilometers. Let's call this side down here hours. When we find out a rate, we're figuring out, again, the change in y over the change in x, the change in kilometers over the change in hours. So delta y, in other words, we're figuring out what this change is here between this y value and this y value here over delta x. And so that change in y, well, how can we make that more exact? So what would be, what's the value of y here? Well, we said it was 8. So let's do this. We'll say slope equals, we said it was, our first value was 8 because we're subtracting this, subtracted from, well, what was the value of y here? Well, the value of y here was 4, right? So we have 8 minus 4. Because we want to figure out what the difference is there. We want to figure out what the change is between those 2 points. And then what was the change in our x values? Well, over here, we're always going to take the one that's furthest to the right first. Over here, the change in x was, well, our x value was 9. Our x value was 9 minus, and what's the x value over here? 3. Or in other words, to figure out how many squares fit in between here, we need to take whatever is here, the furthest one minus the closest one. And if you do that, you figure out that there's 1, 2, 3, 4, 5, 6, right? That's what you get. So let's plug this in, and we get 8 minus 4 is just 4. 9 minus 3 is 6. 4 out of 6 we can make simpler by dividing by 2. We get 2 out of 3. Or if you do 2 divided by 3, you can get the decimal, which is just 0.66, repeating. And then what's our units here? What are we dividing? Well, we divided kilometers over hours. So 0.66 kilometers per hour. Okay? And this is the gist of calculating slope. Let's do another one. Let's do another one here. Let's do another. This is really annoying that's not copying that grid. Here, let's do one as a word problem. So we have example 1. Let's do example 2. What's our time at here? Let's double check. And shoot. Okay. This might be a bit longer than what I said. Example 2. So calculate the slope between points. And let's say that we have the point 0, 12, and let's say 4, 7. 0, 12, and 4, 7. Okay. Well, instead of, what's nice about this one is that we don't have to graph this. We're already given 2 nice points that are on the line. So what we're going to do, we're going to plug in our slope formula. So we said that's slope. And remember, what we do is we take our second y value and subtract it from our first one. So what we're going to do, let's actually give these numbers here a name. We can call this x, or value of x1 and y2 and y1, sorry. And our second coordinate here we can call x2 and y2. And we're going to get a generalized kind of formula out of this. So we can say, well, slope, we take our second y value and subtract it from our first. So it was 7 minus 12. And then we get our second x value minus our first. And that equals 7 minus 12 is negative 5 over 4. Negative 5 over 4. Okay. And you can convert that to a decimal if you want, or you can just leave it as the slope. This is fine as well. So that's our slope for this question. And so we can make a generalized slope formula. And what we're going to say is, so we can say general slope formula. And it says slope equals, and what we're going to call it is, we're going to say that it's y2 minus y1 over x2 minus x1. So if we go back up to this question up here, we had our 2 points here, our furthest left point and our furthest right point. This, if our coordinates here, this represented our, well, we'll start down here. This was our x1 point. This was our y1 point. This was our, up here, this was our x2 point, and this was our y2 point, okay? Oops, and that's all we plugged in over here, right? y2 minus y1, which is 4, and then x2, 9 minus y1, or x1, sorry, 3. And we divide those out. Same thing up here. We get our y2, 7 minus y1, 12, x2, 4 minus x1, 0. And so we just have one more thing that we need to cover here. And I will import it as a question here. And let's look at example. This is example 6 from the note package that I have for this. It's not technically example 6 for this. This is actually example 3, right? So the slope of a line is 5 over 8. And if the line passes through the points, we're given 2 points here, 1, 2, and 33a, we need to find the value of a. So let's recall our slope formula. So slope equals, let's do y2 minus y1 over x2 minus x1. And since we have a bunch of variables here, let's label these variables up here, okay? So for our first coordinate, this is going to be x1, this is going to be y1. For our second one, this is going to be x2, this will be y2. And for a slope, this equals our slope, right? So let's plug in. I'm going to take all these values up here. I'm going to plug them into our formula down here. So when I see x2, I'm going to write 33. So let's do this. So our slope is actually 5 over 8. 5 over 8 equals y2. What did we say y2 was? Well, y2 we said was a. So let's just plug that in. A minus y1, which is 2, over x2, which was 33, minus 1. So this might look ugly. You might be freaking out saying this is not possible to solve. But let's do this just using the low-hanging fruit. Simplify what is easiest to do right off the get-go. And what can we simplify? We can't do anything with this, right? But we can do 33 minus 1. Let's just do that because we know what that is. That's 32, right? Over 32. And we want to find the value of a. So we need to start figuring out how to get a on its own. So what can we do? What's the easiest thing to move on this side to start getting a on its own? Well, what I would do is get rid of this 32. And since it's being divided by 32, we need to multiply by 32. So times 32 on both sides. And then you notice these will cancel. And how do we deal with it over here? Because pretend this is actually a fraction. This is just 32 over 1 times 5 over 8. Well, notice we can ask ourselves, how many times does 8 go into itself? Well, it goes into itself 1 time. How many times does it go into 32? It goes into 32 4 times. So we're actually, instead of 32 times 5, we have 4 times 5, which is nicer than a. So we have 4 times 5, which is 20. And then remember, we canceled out that 8, so that it would go into the 32. So we only have 1 on the bottom here now. So it's just 20 over 1 equals a minus 2. Well, 20 over 1 is just 20 equals a minus 2. What's the easiest thing now to get rid on this side? We need to get a on its own. Well, we can add 2. We can add 2. 2 plus. And what do we get? 22 equals a. So therefore, our 2 points are 1, 2, 1, 2, and 33, 22. So that's the gist of it. I will only give you questions that are surrounding these type of questions here. I hope everyone has a good week and has had an amazing weekend. We will reconnect on Wednesday. Okay, take care, everyone. Bye.